Hello to everyone. In the last class, if you remember, I have discussed the considerations regarding particle beam. So, basically we are discussing the experimental aspects of nuclear astrophysics, isn't it? So, in the last class we have seen how many types of accelerators are there and what should be the considerations regarding the particle beam and how charged particles and neutrons can be generated. In today's lecture, we will see one problem which discusses the effect of small shift in the particle beam's energy on the cross sections of the nuclear reaction. So, by now it must be clear to you, any experiment related to nuclear astrophysics, they are basically centered around the measurement of cross section, because it is the cross section of the nuclear reaction which gives the information about the rate of the nuclear reactions by taking its product with the velocity sigma into V, isn't it? And from the reaction rates, researchers finds the abundance evolution, and also from the cross section, the energy production in the stars, its lifetime, all those things can be analyzed, though Q values are sufficient to find out the energy emitted from a nuclear reaction. So, the center of the discussion on experimental aspects of nuclear astrophysics is the measurement of cross section. Will there be any change on the measurement of cross section if there is a slight change in the accelerator beam energy? So, we will discuss one numerical. After that, we will discuss another important aspect of the experimental nuclear astrophysics, that is target materials. In the star, when nuclear reactions are happening, there is nothing like projectile and target. When reaction is happening between two nuclei, which one is projectile and which one is target, it does not matter. But can we create that kind of situation in Earth's laboratory? No. So, you have to perform nuclear reactions using particle accelerator. So, after particle accelerator, the second important component in the nuclear astrophysics is target materials. So, in today's lecture, we will see what are the target materials and associated equipments which we should understand before planning for any experiment. All right. So, target materials, what are the backing materials, target chambers and the target holders. So, all these things comes under the targets, isn't it? So, let me discuss, as I said, the problem related to the measurement of cross section when there is a change in the particle beam's energy. So, let me show you one interesting paper which I came across, and this paper is from one of the important experimental facility in the world, that is LUNA, Low Energy Underground Laboratory for Nuclear Astrophysics, laboratory for underground to carry out the experiments related to nuclear astrophysics, LUNA collaboration. So, LUNA collaboration has come up with wonderful experiments and they reported data related to lot of nuclear reactions relevant for nuclear astrophysics. So, in this particular paper, you can see preparation and characterization of isotopically enriched tantalum oxide target for nuclear astrophysics studies. So, here what they have done, let me quickly read the abstract. So, they have measured the cross sections at astrophysical energies, right, which often requires the use of solid targets of known thickness, what is the composition of isotopes and what is the stoichiometry, which is one of the main challenges, and I will discuss the role of stoichiometry of target material also in today's lecture. But in this particular slide, I am showing you an interesting experiments carried out by LUNA collaboration. So, any target material when you consider, it should withstand high beam currents for extended periods of time, because it is not like you are doing the experiment for half an hour or 1 hour and you got the enough data and you can analyze the data and measure the cross section. So, you need to take the data for long time in order to reduce the statistical uncertainty. So, for long period of time one has to acquire the data. So, in this paper they have reported on the production and characterization of some target tantalum oxide for the study of proton induced reactions at the laboratory for underground nuclear astrophysics, as I said, right. It is placed in Gran Sasso, and here the targets are prepared by anodization of tantalum backings. Why tantalum is preferred over other materials, that I will discuss. In enriched water up to 66% oxygen 17 and 96% in oxygen 18. So, whenever you come across language like this, so it is clear that incident beam is proton and the target material is oxygen. So, we are carrying out a nuclear reaction in which projectile is proton and target is oxygen. Here we have two isotopes, oxygen 17 and oxygen 18, right. And in this particular example, when they have measured the they have cross section, the target thickness was monitored during this heavy proton beam bombardment by performing thick target yield measurements of the well known resonance at laboratory energy of 151 keV. So, from this what we can understand? During the course of the experiment, you have to ensure that the thickness of the target is changing or not. What will happen if the target thickness changes? Of course, there is a huge change in the yield, and after some time it can evaporate as well. So, when you consider in nuclear reaction, it is important to monitor the thickness using various methods, and here they have adopted a method, that is thick target yield measurements, and there is a well known resonance at laboratory energy of 151. You can calculate the Q value of this reaction, that gives you the energy of the resonance in the fluorine 19, and they have observed a linear decrease in thickness as a function of the total accumulated charge observed for some time. Now, you can see here, you see energy on the x axis, yield on the y axis. You see here it is almost constant around at 0.21, isn't it? And after say 165 keV kind of thing, the yield is decreasing, isn't it? Why it is happening so? The decrease in the yield of a nuclear reaction shows that the target thickness is changing. So, you have to see after which laboratory, which energy the thickness is undergoing a change. And here the yield, when I said, it is the yield of the gamma rays emitted when proton interacts with oxygen 18, and the lab energy is at this particular time it is 151 keV. So, this is one method which shows how to monitor the target thickness, all right. Now, in this let me consider the resonance energy 151 keV, all right, and 143 keV if the proton beam has, okay, and we are considering a resonant reaction. What I am trying to discuss in this slide? The aim of this discussion is to see the change in the cross sections of the nuclear reactions when there is a slight change in the energy of the projectile, and here initially if I consider the projectile energy as 143 keV, okay, in the center of mass system, and I am looking for the resonance at 151 keV, then consider that temperature 0.06 gigakelvin, or you can also write this as T9 is equal to 0.06, both are same. Remember, whenever you perform any nuclear reaction experiment, you have to quote the corresponding temperature as well, because already you have seen many times the impact of temperature on the performance of any nuclear reaction. So, here the temperature considered is 0.06 gigakelvin, isn't it? So, I am considering here 151 keV resonance in this reaction. For example, there is an error in the measurement. There is an error in the measurement that 148 keV, where in the resonance energy. If there is an error in the measurement of the energy, remember the detectors which we use for the calibration of the nuclear reactions, there if we report there is an error in the energy like say 3 keV. So, ER is equal to 151 keV, this we are looking for, but assume that we are reporting as 148 keV, then what will be the change in the cross section, that we are trying to understand. Okay. So, here the number, that means reaction rate per particle pair multiplied by this. So, ER minus delta E if you consider, and the reaction rate for ER. Okay. So, you know it is e to power of minus 11.605, the formula already have discussed, and instead of 140, it is 143 keV now, minus there is a difference of say 3 keV, so 0.143 MeV, and this is divided by 0.06 because it is a temperature. Now, it is e to the power of minus 11.605 minus 0.143 divided by 0.06. Now, if you see this 1.80 you will get. So, for a slight change in the projectile energy say by 3 keV, the change is about 80%. The change is about 80%. So, you can imagine the accuracy with which the measurement has to be carried out. So, this is about a resonance reaction. This is about resonant reaction in the proton on oxygen 18. Now, let us see the non-resonant reaction. By now, it must be clear to you what is the difference between resonant and non-resonant reaction. So, whenever I say resonant reaction is analyzed, one has to mention the energy of the resonant state, whereas in the case of non-resonant reaction, it is sufficient to mention the projectile energy, because non-resonant reactions in general happens with all incident projectile energies. All right. Now, what if the non-resonant reaction proton on oxygen is considered? Here the compound nucleus is F17 and the projectile energy, if I take in center of mass system, if it is 100 keV, then instead of 100 keV, if I perform at 103 keV, what will happen, right? Earlier, instead of 143, it is performed at 148. Okay, sorry. So, earlier I said it is 151 keV. No, basically the projectile energy in CM system was 143 keV, and error in the measurement if you perform at 148 was discussed. Now, here instead of 100 keV, if the measurement is performed at 103 keV, what will happen to the change in the cross section? So, do you remember the formula which have to be used in order to calculate the cross section for a non-resonant reaction? So, let me write down. So, it is basically the cross section for non-resonant reaction is 1 by e to the power of minus 2 pi Sommerfeld parameter and S value. Remember here the S value dependence on energy is not considered, and 2 pi eta if you see 0.989534 Z0 Z1. Here Z0 is 1 for the proton and Z1 for the oxygen is 16. All right. And here 2 pi eta is given by 1 by E m0 m1 divided by m0 plus m1. Okay. Now, the cross section for E plus delta E. What is E made here? The E is 100 keV, and what is delta E? It is 3 keV. So, here I am considering the effect of change in the projectile energy on the cross section. So, here the delta E is 3 kilo electron volt. So, in the denominator you have sigma as a function of E. So, 1 by energy is here 1.103 and exponential if you take minus 0.989534, okay, and multiplied by 1 multiplied by 8, it is basically 16 multiplied by 1, 16 plus 1, 1 by 0.103. So, I have written expression for cross section of the non-resonant reaction when the measurement is performed at 0.103 keV. All right. So, here it is for E 0.100, is not it? Exponential minus 0.989534 into 1 into 8, same 16 into 1 by 16 plus 1. Instead of 0.103, now it is 0.100. All right. So, if you do the calculation, it is 1.4. What does it mean? The change in the projectile energy by 3 keV has resulted in 40% change of the 40% change in the cross section of the nuclear reaction. In case of resonant reaction, it was about 80%. In case of non-resonant reaction, it is about 40%, just by changing the projectile energy by a few keV. So, especially for charged particle induced reactions, it is very important to ensure the accuracy in the projectile energy. So, this example must have cleared the role of accuracy in the projectile energy while measuring the cross sections. Remember, one of the important assumption which has been made is the dependence of S factor. All right. So, from this numerical, what we have understood, the slight change in the projectile energy can cause huge change in the cross section of nuclear reaction. So, while doing the calibration of the particle accelerators, it is very important to ensure the excellent accuracy in the projectile energy. So, this is all about particle accelerators and the beams, what should be its diameter and what should be its resolution, what should be its accuracy in the energy, all these things we have discussed until now. So, as part of the experimental aspects of nuclear astrophysics, let me go to the next topic after particle accelerator. More details you can read in the textbooks like Cauldrons in the Cosmos by Rodney and Rolfs, and the introduction to nuclear physics in the stars by Eliadis, and there are many more textbooks. So, more details about the particle accelerators, how do they work, you can only also, you can always go through the textbooks. Here just I am trying to give you an overview of the particle accelerator and what is the importance of projectile energy on the cross section. All right. Let us go to the next topic, that is targets and associated equipment. It is already clear, in order to understand the energy production in stars and synthesis of elements in the universe, these two are the main goals of nuclear astrophysics course. So, of course, it is very important to perform nuclear reactions in Earth's laboratory using particle accelerator. And like in stars, we cannot create a environment where nuclei undergoes reaction with each other without considering the projectile and target concept. So, until now we discussed particle accelerator, which takes care of the projectiles, and now let me provide a brief overview of the targets. So, when I say targets, so I am not only confining to only the target with which the projectile is reacting, so that nuclear reaction happens. Here I am also including the associated equipment. What do you mean by that? See, when a particle beam falls any target, you cannot just hold the target in air just like that, right? You should have a chamber. Of course, this will not be there, okay? And here you should place target above some target holder, isn't it? There is some target holder, then you should have some kind of backings. Many a times it is important to have a supporting material for the target to stay there during the nuclear reaction. So, which we are calling as backings. Okay. So, you need to have target holder, you need to have target chamber, you need to have backing materials. What are the considerations related to these targets and associated equipment. Remember, the discussion on target materials is centered on charged particle induced reactions which plays important role for the energy production in stars and synthesis of elements in stars before the iron, and neutron induced reactions which play a role in the energy production in stars and synthesis of elements via S process, R process, that is beyond iron peak. So, whatever considerations we are discussing right now, one should keep in mind charged particle induced reactions and neutron induced reactions, and what kind of target materials are preferred, and holders are preferred and chambers are preferred. So, let me start the important considerations of the targets and associated equipment. All right. Of course, it depends on the thickness of the target material, and depending on the nuclear reaction of interest, either one can go for a thickness of target which is such that ion beam can pass through the target material. So, the thickness is such that it is thin enough that ion beam passes through the material. Then for charged particle induced reactions and neutron induced reactions, what kind of transmission targets are preferred, whether do we require the holders and backing materials or not, those things we will see. Sometimes, depending on the nuclear reaction of interest, the thickness is in such a way that whatever beam is there, it is completely stopped within the target material. So, I have given a name beam stop target and a transmission target. So, the synonym for transmission target is thin target and beam stop target is thick target. Though thin and thick, they are of course relative. All right. So, from now onwards, when I use the word transmission target, it means it is thin enough that ion beam is able to pass through it. And whenever I use the word beam stop target, as the word literally conveys, the beam is stopped within the target material. All right. So, I am dividing the targets into two types, transmission and beam stop targets. Which one has to be selected? As I said, of course, it depends on the type of nuclear reactions that we are considering. Not only that, it also depends on the observables to be measured. What do you mean by this? What do you mean by the observables to be measured? Consider the triple alpha reaction. If you remember, alpha plus alpha plus alpha gives rise to 12C. Of course, it is a two-step process. In one step, alpha plus alpha gives rise to beryllium 8 and beryllium alpha gives rise to carbon 12, isn't it? So, in this triple alpha reaction, if we want to measure the cross section, then the carbon 12 has to get disintegrated into 3 alpha particles, right? So, accordingly, the detectors have to be chosen. Only detectors? No, even the target materials also should be designed in such a way that alpha particles should not lose energy, much energy within the target material. So, that is what I mean when I said the selection of the target materials depends on the observables to be measured. If you want to measure the gamma energy, then accordingly target thickness can be considered. If you want to measure the scattered projectile, accordingly the target material has to be chosen. So, not only in the type of a nuclear reaction, but also on the observables to be measured like scattered particles, in this case protons in the previous example that we have seen, and gamma rays and sometimes alpha rays, sometimes neutrons. So, all these are observables I am saying. Okay. Now, just consider one of the major reactions type that we come across in nuclear astrophysics, that is capture reactions. When I say capture reactions, it could be induced by neutrons or protons, and capture reactions, if we are also can be further divided into radiative capture and non-radiative capture, right. As I have said in previous classes, radiative capture reaction means the ejectile is the gamma, right. Now, there should be little attenuation for gamma rays. If you consider P gamma or if you consider alpha gamma ray, alpha gamma base reaction, the target should be in such a way that there should be very little attenuation for the gamma rays, right. Considering this, normally the backing materials are chosen such that the thickness is in between 0.5 to 2 millimeter thickness. Why? Why only this thickness? Why not beyond this? You know how gamma rays travels to the matter. I is equal to I naught into e to the power of minus mu t, where t is the thickness, mu is the attenuation coefficient, I is the incident intensity, in this case gamma rays, and I is the intensity after passing through the thickness t, right. So, the thickness of the backing material should be in such a way that there should be little attenuation of the gamma rays. When I consider radiative capture reactions, isn't it? If there is a huge attenuation, what will happen? We are losing lot of gamma rays. The count rate in the nuclear reactions will be less. And there is a beautiful advantage when the thickness of the backing material for the target material is chosen in such a way that if it is above 95% transmission for the gamma rays, what is the advantage? Can you imagine? See, when now let me draw like this just for difference. It is the projectile and it is the target material, and this is the backing material whose thickness I am saying it should be in between 0.5 to 2 mm, and you have say chamber, target chamber. Okay. Now, I can place gamma detectors at any angle of my wish if I have enough money, and if I have good number of detectors, I can afford to place detectors behind the target material, sides of the target material, because the thickness has been chosen in such a way that there is a very little attenuation of gamma rays. All right. So, little attenuation in this backing material allows detectors to be placed at any place, so that we can get large number of counts. So, for radiative capture reactions, the question is what should be the thickness of the backing materials? It should be of the order of 0.5 to 2 mm thick. Of course, it depends on the energy of the gamma rays. For example, if it is 0.5 MeV, then it is 95%, I mean 90%, and if you go for like 5 MeV or 6 MeV kind of thing, the attenuation is very less. So, more than 95% gamma rays will pass through the backing material. Remember, when particle is interacting with the target, this is target material and this is a target backing. If gamma ray, good number of gamma rays gets absorbed in the backing material, as I said, we have to place detectors only in front portions of the nuclear reaction, the place at which nuclear reactions are taking place. Okay. So, these are some of the important considerations for the backing materials when we discuss the target materials. So, we will see more about the target materials and preparations of the backing materials, all right, and chambers and target holders, what are the arrangements to be done in the next lecture. Thank you very much.